好，那我们继续开始上课。Okay, so continue the capture analysis. Okay. A little bit recap on capture analysis. The capture analysis basically comes from the idea of homomorphic filtering. Okay, so it's an application of trying to find a new domain such that the low and high frequency component, their multiplication in a particular domain that can be linearly separable. Okay, but the idea it really is behind the homomorphic filtering. Okay, so here a little recap. So if you have a signal Y of n that's an actual signal, some low frequency signal plus some noise high frequency. So in the spectrum, as things is easy, right? You just take the spectrum and the low energy part will go to the lower part of the spectrum, right? The high energy part will go to the higher part. The noise part go to the high frequency component, and you can properly design filter, right? Go with low pass filter, band pass filter, high pass filter to filter out the component that you want. Okay. So in this case, we call this kind of things, this signal and noise spectrums are separate linearly, and those are the things that you typically learn in a DSP, in a basic signal system where things are additive, low frequency noise, low frequency signal plus high frequency signals, and you can do filtering to lift it out. Okay, so what if you have signal that's XFN convolving with U and say the signal is low frequency, but it's convolution to the U of n, which is some excitation noise or some high frequency noise. So can we find a new domain that makes them linearly combined or linearly separable? Okay, so the whole idea behind capture analysis is trying to find a new domain called capture domain that's able to process this kind of signal as though they are additive. Okay, so that's the whole sort of basic idea. Okay, and that domain we call it capstrom domain, and it's a made-up word. Okay, there's no actual word called capstrom. It's a swapping between SSC, so it's a spectrum swapping that becomes capstrom. Okay, so we'll talk about introduction to homomorphic filtering. So we already know in terms of LTI signal system that linear systems satisfy simple superposition. Well, that's the definition of linearity, right? When two things add, okay, if you apply a system onto the thing, as though you're applying individual component through the system and add it up. Okay, so that's superposition. That's the definition of linearity. Okay? So that kind of terminology we call homomorphic to addition. Okay, it doesn't change with respect to addition. So if the signal has additive component of two things, you can operationally operate on individual component and add it up. Okay, so we call that homomorphic to addition. So in the standard LTI system, right, Xn goes through LTI system Yn. If Xn is two things that's additive, the Yn are individually processed through and get back to the original ones. So in case of speech signal or in other signal where you have things that are convolution between excitation and vocal tract filter, if you want to have a system design that can have this superposition effect, but it's more of a generalized version. So for example, if your output signal is two signals that are convolution with each other, if you apply a system onto it, you want to design a set of filter that as though you're applying onto individual component and then convolving with each other, right? So again, this is a generalized superposition. This is a linear superposition. Okay, so in terms of speech, we want this because we already know in terms of speech production, it's your long, exciting vocal cord opening, closing that's resonating through your vocal tract system, and then those things combine. Imagine it as a source filter system, then you get an output. So if we can find a filtering approach that actually operates on individual components as though they can be done separately, and then that's a good sort of a system analysis. Okay, so again, so we can represent that entire process, right? So if your X of n is originally something that's convolving through some functions, okay, it goes into a new domain that makes them additive. Okay, now you have to design a linear filter in this case that you can process them individually, then coming back from the inverse of that particular characteristic function or some transform, right? Then you get back to the original one as though they're convolution. So this D, we call it a characteristic system for homomorphic deconvolution. The idea is trying to convert convolution to addition. Okay, if you can convert convolution to addition, then then whatever LTI system that you know about, then you can design linear filter in that particular space as though you're carrying out regular linear filtering. Then you just need to do an inverse cutback. Okay. We call it X prime, and then this new domain, we call that complex capstone. Okay. So idea is very simple. So take some Z transform or Fourier transform X of Z equals X1 Z X to Z. Please note in this lecture we interchange Fourier transform and Z transform quite a bit. Okay, Z transform usually you utilize more in terms of analyzing systems, discrete systems, discrete signals, but they are essentially equivalent for the sake of this purpose. Okay, so take Z to the e to the j omega, then these two things equal to each other. So we utilize them sort of interchangeably. But anyway, so you have X of Z are these two things multiplication, because original time domain convolution. Find X of Z, make them into addition. Okay, how do I make things from multiplication to addition? You just take a log. Okay, so that particular capstone domain is by taking the log of some Z transform or some spectrum transform of your original sequence. Okay, because this Z is a complex number, so what we have is log of XZ is the log on the real part of psi theta and log the absolute value or the R tangent of Z. So again, because the Z transform Z variable itself is a complex number, so the log of that you have to operate individually on the real part and the imaginary part. Okay, intuition. Give me a second. Okay, so the intuition behind utilizing this kind of idea for speech signal is shown here. Okay. So we take a speech signal and then do a Fourier transform. You plot it, plot the magnitude. It looks something like that. Okay. Again, we hypothesize that using our speech production knowledge, right? Source exciting filter, right? So basically, in a spectral domain, you have these two things multiplying each other, where it has a sort of excitation response that's sort of fast variation when we look at it in a spectrum domain, multiplied by some slowly variation where the peaks associated with the former structure, which is the resonance of your vocal tract. Okay. So by taking the log, right, and it's a smart thing, right? So if you never thought about it, right, the log, this particular operation, right, just simply taking a product of two things into summation. Okay. What effectively it's doing is basically scaling the value. Okay, right? Log is a process of scaling value. Okay, so you have two things originally multiplied, now they become addition. Okay, basically the difference is really the scaling of that value. And a log takes that scale out and then say, okay, let's take my multiplication into a summation. So that's pure mathematics. Okay, by simply scaling the values of things that makes them come from two multiplication results become two additions of results. Okay, so otherwise, you think about it, taking the log of the spectrum. In reality, what you're doing is just scaling the value of that amplitude. Okay? But the effective of doing that is taking that product now becomes a summation. Okay, a summation between these two numbers. Now we just need to find a new domain that try to make the high varying signal and the slowly varying signal become nearly separable. Right? So we already know how to do that, right? So imagine this is a time domain signal with high frequency plus low frequency. What you need to do is probably take another Fourier transform or take another spectrum transform. You'll move slowly varying part to the beginning, okay? The high varying part to the upper part of things, okay? Then basically you just need to design your filter, or in this case we call lifter operation, to lift out the part where you want. Okay, so that counts this kind of process. Okay, let's look at actual definition. So the definition of complex comes from the various version. Okay, some people write it as Z transform, some people write it as Fourier transform. Basically, they're interchangeable. Just need to take Z to e to the j omega. You'll see they're equivalent. So inverse Fourier transform of the complex algorithm of the power spectrum of the signal. Okay, so very simple. This is the capstone domain, right? Inverse transform, right? Inverse transform and Fourier transform, I don't think they're different. It's had that minus sign, e to the j omega, right? So if you know that, so forward and backward, they're essentially the same transform. that has a negative sign explanation. Okay. So for inverse Fourier transform minus pi to pi x prime x e to j omega e to j omega and d d omega. So what's this? This is just a log, right? The operation that we're talking about, the log of the spectrum, right? The complex law. So it has a magnitude part and an imaginary part. Taking the inverse Fourier transform and you get to the domain. We call the Capstrom domain. Okay, so you can prove this fairly easy. If x of n is real, your complex capstrom is also real. The real capstrom is the even part of the complex capstrom, right? So take the x hat of n plus x hat minus n divided by 2, which is this part essentially just the magnitude portion of the original spectrum taking log, taking the inverse. Okay, so if you have a real signal, okay, you know this is real. With a real signal, you can compute the real capstrom. So the rest of the values are becoming real. Okay, so these are the actual coefficient. Later we'll talk about the capstrom coefficient, essentially what people are computing. So, but effectively it's taking a log of the spectrum and then do another inverse Fourier transform. Okay, so like I said, the inverse Fourier transform is the only thing that's different here, right? There's a minus sign in this case. So what you effectively do is still take the log of the spectrum, okay, do another Fourier transform. That's basically what the capstrom is doing. Okay, so this particular process, taking a log, making sure the values in this original case, if things are multiplicative, becomes additive. Okay, that log operation helps you do that. Take another Fourier transform or inverse Fourier transform helps you to move the slowly varying part up to in the new domain to the beginning portions of the n. Okay, and the fast variation part to the later part of the n index. It's like a Fourier transform. The low frequency versus high frequency. Here we just call the low Q-frequency, right? Again, this is swapping between F and Q. Okay, low Q-frequency part and the high Q-frequency part doing this kind of Fourier transform. Okay, so conceptually, it's very should be very intuitive. Okay, two things convolving in time domain becomes two things convolving in the frequency domain. Taking a log, they become additive. Taking another Fourier transform, if your additive signal has one is highly varying and then one is slowly varying, they will move into the front part or the later part. Then you can design your filter coefficient accordingly. Okay, so that's kind of the whole process. Okay, we can talk about various properties of the complex capstrom. Okay, like I said, oftentimes, when we first design it in terms of the in terms of the Fourier transform, we usually analyze with respect to Z transform. They're particularly related. Okay, so again, Fourier transform is just a Z transform, but you only look at the amplitude of one around the circle, right? So everything else are the Z plane. Okay. We can write any particle C time series model, discrete time series model as this particular form. Okay, so again, some G of k from 1 to n1 minus alpha k z minus 1, k from 0 and not 1 minus bkz. Okay, k from 1 to n not 1 minus ckz minus 1, k from 1 and not 1 minus dkz. Okay, it depends on right. This is z minus 1 and z minus 1 here, z minus 1, z minus 1. Okay, if you compute them, this will find the ck where this increases to 0, find the ck where this increases to 0. This thing we call poles, right? This thing we call zeros. Okay. If you have form like this, okay, your poles and zeros are inside the unit circle. Okay, if you have poles and zeros are inside the unit circle, we're known as a stable system, right? So again, refresh your Z transform analysis section in your DSP course. Okay, when we do Z transform, we find a region of interest, a region of convergence, whether your pole locations are inside the unit circle or extend to each external side of the unit circle. That depends on original time series where it's going to become the unstable time series or stable time series, or it's just simply oscillating. Okay, if you have poles, right, around, if you have poles, you remember if you have poles exactly sitting on the unit circle, what it does, right, it has no decay, it also doesn't increase because the poles are either inside or outside or on your circle. On your circle, you have a complete oscillation signal. Okay, it's non-convergence, but it doesn't go out of bound. It also doesn't converge. Okay, it always oscillates. Okay, so depending on where your poles and zero place, it tells you the shape of the time series model. Okay, let me repeat. So if you have BK and DK, if you find the poles and zeros are here, there tends to correspond to the pole outside of the unit circle. Okay, so one would be a causal signal and not be a non-causal signal. Okay, so anyway, so any time series model we can write in this particular form. Okay, take the Z transform of any time series model. Any time series is just any discrete time sequence, we call it time series model. In a discrete sequence, you can always write the Z transform in terms of either poles inside or outside, okay, whether it's zeros or poles. Okay. Now, by looking at the power series expansion log, now log of y plus x is something like this: x minus x squared divided by 2 plus x2 divided by 3 minus x squared. This is like a Taylor series expansion. Okay, these are things you probably learned in calculus. Okay, remember this expansion series of log. Okay, so what we can write then is the capstone, right, is a inverse transform, right, because we work in the Z transform, the inverse transform of the log of the transform. Okay, right. So if we write them in this particular manner, okay, then we can actually write out three different parts. X hat of n equals to log of g when n is at particular this n index, the capstone, the Q frequency index. Okay, so x prime of n plus log of g equal n goes to 0. When n is greater than 0, okay, you have the k from 1 to n minus I think these are the zeros, and this is the poles, right? No, sorry. Yeah, this is the poles. This is the zeros. This is the poles. Okay, minus k from 1 to n minus I alpha k n, where n is greater than 0. Or if it's only the other side, that's you have k from 1 to bk minus n minus k from 1 to n not dk minus n for n is less than 0. So again, complex capstone in general form is non-zero, infinite, then two-sided. Right? So it goes to negative infinity, goes to positive infinity, also at 0. It also is a decaying sequence, okay, bounded by beta a to the n power divided by n, where this alpha equals the maximum of one of these values. Okay, so it's a bounded signal. Okay, so let's look at one particular kind of a useful time series signal. Okay, minimum phase. Okay, recall how do we know a discrete sequence is a minimum phase signal? If you plot the Z transform, all the poles and zeros are inside of the unit circle. We know that the system and its inverse are always causal and stable. Okay. Effectively, most of the system we design in real life. Okay, when we teach you math, we teach you everything. Okay? But in terms of the actual engineering system, they will actually work out in real life and in real life systems. They are usually minimum phase. Their poles and zeros are inside unit circle. The system and inverse are always causal and stable. If you have a system that's non-causal, it's very hard to operation, right? If a system is non-stable, when you have the system on overtime, it's going to explode. So usually you design a system, okay, it's a set of operation onto your signal that are always causal and stable. Okay. So in this case, your complex capstone, okay, equals to 0 for n less than 0. So it's a causal. It's also a causal sequence. Okay. If you have a minimum phase time domain signal, okay, your complex capstone called that particular time series is also causal, where n is less than 0. And of course, it completely specified by the log magnitude of the spectrum. Okay. No phase information in this case. Okay, we'll talk about the recursion for computing x hat in this case. Okay, so the recursion for computing x hat when x hat equals to 0, but n is less than 0 because it's a causal sequence. Nothing happens for index that's negative. Okay. Log of x0, okay, at n equals 0. The rest of them follow this formula. We'll derive this formula in a bit. So x of n divided by x naught divided by k from 0 to n minus 1, k divided by n, x hat of k, x n minus k, x naught. Okay. So if your x of n, the original signal, is maximum phase, okay, that means it's a causal and a stable at just maximum phase. If it's inverse, causal and stable. Okay. Usually you don't design system like that. Okay. But anyways, we will see how this recursion computation occurs in this case. Okay. Let's compute for minimum phase signal. If we want to compute the capstone coefficients for a minimum phase signal, how do I compute them? We can utilize this recursion formula. Okay. We'll look at the recursion formula derivation. Okay, let's derive something. Okay, x prime z. Let's take them as log of x of z. Okay, so log of x of z. Okay, so let's take derivative on both sides first. Okay, d dz x hat of z. Take derivative of this thing or d dz log x of z. That equals 1, right? When you take derivative out of the log, you have 1 over xz dxz dz. Okay, so when you have d dz x of z equals to 1 over xz dxz dz. Okay. Now you multiply both sides by minus z here, okay, or z here. Okay, here in this case you multiply by minus z d dz x hat of z equals 1 over xz minus z dx dxz dz. Okay, now you have this term and this term multiply 1 over xz. Take this x of z over here. Okay, try to do an inverse z transform. Okay, you have a z multiplied by this thing. Okay, the inverse transform of this thing equals to n times. We know the inverse transform. We know the inverse transform of this thing. Okay, is x hat of n. Okay, so this is x hat of the actual complex capstone, right? Z the inverse of the x bulk of xz. Okay, that's this thing. Okay, multiplied by the x of z. No, z transform, inverse z transform of those two things multiplied becomes a multiplication convolution, then becomes a convolving with x of n equals to n x of n. Okay, so now let's expand this term. Okay, summation of k from minus infinity to infinity. Okay, k times x n minus k. Okay, let's just write out the convolution equals to n x n. Okay, now we can continue. Okay, sum from k from minus infinity to infinity, k x hat of k, x n minus k equals n x n. So we can write x of n equals to this particular form. Okay, sum from k from 1 minus infinity to infinity, k divided by n x hat of k, x n minus k. Okay, so we now derive the original signals index at nth position equals this particular summation. Okay, now if the x of n is minimum phase, okay, we know that n minus k has to be greater than equal to 0, n has to be greater than equal to k, and k also has to be greater than equal to 0. If my original time series x of n is a minimum phase signal, then we do have this index follow this criterion. Okay. Once you have that, then let's look at the process. Okay. When n equals to 1, right? When n equals to 1, k can go from the minimum is 0, right? Can go from 0 to 1, right? So x1 equals to k from 0 to 1 summation, right? K divided by n, x hat of k, x n minus k, right? So we know x1, right, equals to, let's plug in k from 0 and k from 1, right? The k is to 0, then this whole term goes to 0. If this k equals to 1, then it's basically just x1 equals to 1 times x hat of k times 1, right, minus 1 minus 1, so that's x of 0. So now have x of 1, the original time sequence index at the first position equals 1 times complex capstone coefficient at the first position multiplied by x of 0. Okay, so x hat of 1 equals to x1 divided by x0. Okay, that's how we compute the first the first complex coefficients of minimum phase signal, okay, which is a lot of signal that we have in real life, which is the x1 divided by x0. Okay. Now look at when n equals to 2. Okay. Now we have x of 2 equals to k summation can go from 0 to 2, k divided by n, x hat of k, x n minus k, right? X of 2 then equals to, right? If k equals 0, this term is 0. If k equals to 1, that's just 1 times x hat of 2 times x0. If k equals to 2, k equals to 2, x hat of x hat, it should be here, x hat of 2 times, I think there's a 1 half somewhere. Oh, this is 2, okay, this is 2, so this is 2. So k equals 1 half, x hat of 1, xn minus k, right? Plus, when k equals to 2 divided by 2, that's 1 times x hat of k equals to 2, and x0. Okay, so we know x hat of 1 from here, which is x1 divided by x0. Now we have x2 divided by x0 minus 1, x1, x0 equals to x1 hat. So by this, then you can derive the x2 of hat. So x hat of 2 can be recursively computed once you finish the first one. The third one follows. Okay, once you have the second one can plug into the third one, okay, then plug into the fourth one, can plug into the fifth one. So the coefficient can be computed recursively. Okay, and again, this will speed things up. Okay, because once you have the previous, you can continue to compute the next one. So this recursion formula essentially can be written as this x hat of n, right? The capture coefficient of the minimum phase signal equals xn divided by x0 minus k from 0 to n minus 1, k divided by n, xn minus k, x0, x hat of k, and has to be greater than 0. Then iteratively, we can actually compute all the coefficients of the complex of the capturing coefficients. Okay, we won't go through this, but the same logic can be applied to maximum phase, where when xn is maximum phase, the summation is good for n minus k has to be less than equal to 0, k has to be less than equal to 0. Then you derive another set of recursive computation for your signal. So, okay, let's look at a few special cases. Okay. If your original signal is an impulse train, okay, x of n, okay, is an impulse. Sum from r to 0 to m alpha a, okay, signal m minus r ends up p. Okay, now we know x of z. Again, basically it's just a sub r z minus r and p, because the delay becomes a z minus something, right? The complex capstone, okay, non-zero integers only happen in multiple np, so it can be derived of this. Okay, try to do this derivation. Okay, basically what you need to do is a z inverse log of that. Okay, you'll see that equals to r from 1 to minus infinity minus 1 r minus r plus 1 alpha r divided by r, again with the same delta m minus r and p. So okay, you can think about this as some decaying sequence, oscillating sequence, right? Because it's minus 1 to the first order, second order, third order, fourth order, right? So it's basically the oscillating signs. This is your magnitude divided by that oscillation index. Okay, then you multiply by a delta function that's also an impulse train. Okay, so if your original signal, okay, is periodic, right? Because it has this period of NP. In the complex capstone, you also have the same period. So the complex capstone of uniformly spaced impulse train is also an impulse train with the same spacing. Okay, so if your original signal in the time domain has that spacing, okay, compute it, right? It should make sense, because what you're doing is taking a transform, taking a log, and taking another transform. It comes back to a domain that looks like time but not time, right? Because you're taking a log in between, doing the inverse transform. So you're effectively kind of looking back into the time, but not time, because you have a log operation within it. Okay, but that intuitive should tell you the original periodicity will be preserved. Okay, whatever in the time domain that periodicity is there. Okay, it'll have the same periodicity in the complex capstone, and that tells us, okay, there will be algorithm that design try to detect pitch from capstone, because the capstone will also have this same periodicity as the thing in the original time domain signal. real capstone will have the same behavior as complex capstone. Okay, so basically you have x head of n plus x head of minus n divided by 2. And you just have these two things at the same period, you plus them. You still have the same periodicity within your capstone. Okay, so these are some of the things you want to know. Well, I think intuitively you should. I always think about this process simpler. Okay, don't think about it in terms of a lot of complex transform kind of thing. It makes math looks tedious and difficult. But think about them as doing a complete cycles of transform, back transform, but you stick a log in between, and that's it. Okay, so but this particular operation of that log, okay, is quite unique. It scales the value of the magnitude, so that whatever the signal in the frequency domain originally they're multiplicative, they become addition, and that's the only thing that's sort of think about it outside of the speech processing. Okay, let's don't think about speech, right? You have pick any signal. Okay, take a z transform or a Fourier transform, taking a log on the magnitude, then you do another transform. Okay, supposedly you are getting back the original time domain signal. Okay, but the only thing that's being changed is that particular log operation. And log operation, we know intuitively it's a scaling of the value. Okay, of course, log operation, that particular symbol is a limiting factors of some exponential, right? So, but that operation takes the original multiplicative value, this multiplied by this. If I scale it by log, it becomes this plus this. Okay, that's what math is doing. Okay, in terms of speech knowledge, what we hope it is doing. Okay, we don't know what it's actually doing that, but what we hope it's doing is because we understand speech production from a physics or from a physiological perspective, that we have systems that have source exciting the vocal tract. Okay, this excitation, okay, linear filtering that becomes multiplication in the frequency domain, taking a log and then taking another inverse transform. You get back to the domain where this and this become separated linearly on the scale. Okay, so that's what the capstone analysis really helps us do. So instead of thinking about this capstone, right, as the capstone math domain, some people this is just another time domain kind of thing. But you have a log, you have somehow stick into the frequency domain before you do the inverse. Okay, that's all it's doing. Z transform, stick a log, do a inverse. Okay, you're back to the original discrete time index. Okay, but the only thing that's different, you have a log in between, and that log scales the value. Okay? The reason it scales the value is scales in a way so that if you originally have two signals that are multiplied, they become additive. Okay, that's the whole beauty of math, and then we're applying it in a space of speech technology. Okay, and this whole thing we call it capstone transformation. Okay, capstone domain analysis, capstone computation, and so on, whatever you like to call it. Okay. So there's some practical computation consideration. Okay, either in the Z transform or the original definitions of complex capstone, right? It involves integral, right? Minus pi to pi or 1 over 2 pi, and then do a inverse transform on the Fourier domain. In reality, you cannot really do that. Okay, your computers or a lot of digital signal processing that's involved. So whatever you're doing you're doing a forward transform instead of doing e to a minus j omega. We say that omega is going to be split into 2 pi k and 2 pi k n, right? So depending on the values you're going to sample around the unit circle, right? You split 2 pi unit circle into n equal points. Right? So that's how we operationally, our computer actually perform Fourier transform. Okay? We don't do actual omega here. We do a 2 pi divided by n here. It's implementation of DFT using this kind of operation. Okay, then you take a log on this thing. Instead of doing the inverse transform on the using integration, we do a approximation called IDFT, right? And inverse discrete Fourier transform, and split the 2 pi into n. So again, nothing special about this process. Is in your standard Fourier transform, you don't actually do integration. What you do is in your computer you do a fast Fourier, discrete Fourier transform where you equally space the 2 pi to endpoints. Okay, and when you do inverse Fourier transform, you actually again split that 2 pi into endpoints. points back to the original domain. In the capstone domain, it follows exactly the same logic here. Now you just stick a log into the thing. Okay, so in capstone analysis, capstone domain transformation is nothing but really you take a log in between and that's it. Okay, everything else is the same as though you're trying to do a Fourier transform, any transform and backwards. Okay, back to the original domain, but because of log, you don't call it time anymore. Okay, you call them capstone. Okay, so that's the only thing that's different. Okay, all right. And of course, as we know, okay, this DFTs, right? When you do a DFTs, basically you are sampling around the 2 pi, where now 2 pi creates repetitions, right? You're sampling around 2 pi. That means when you do a transform, a sampling in one domain creates repetition in another domain. Okay, sampling in this time domain creates repetition in frequency domain. Sampling in frequency domain creates a repetition in time domain. Sampling in frequency domain creates a repetition in complex capstone domains. Well, complex capstone domains, because capstone domain is just like time domain with a log sticking to it. Right? So the thing that you know about Fourier transforms, samplings, everything follows exactly almost the same in the capstone analysis. Okay, because they are the same, except you have a log in between. That's it. Okay, so the sampling in the frequency domain creates repetition in the complex capstone domain. So again, effectively, practically, you want to have a large enough n to avoid aliasing. It's like you want to have your FFT have enough points to make sure there's no aliasing back to the original time domain. Very similar. Okay, so these are practical computation consideration. Okay, so again, I want to repeat again. All that math is for speech analysis or for speech scientists. What we really care is again that speech signal. The hypothesis is source exciting filter. Okay, because that source exciting filter concept, the capstone analysis makes sense. Okay, because it helps us tease apart the slowly varying formal structure and the highly varying fundamental frequency harmonic structure. These two things can become separate. So we can analyze this signal as though we're trying to analyze the source part or analyze the filter part. Okay, so later on we know for automatic speech recognition, what we really care is the filter part. Okay, so we will derive coefficients that basically try to compute here and take that as input to design our speech recognition system. Okay, but this whole capstone analysis built upon the idea of for speech, built upon the idea of source and filter. Okay, so just keep this plot in mind. Okay, that's any speech signal under clean setting, you will see always something like that, some oscillations and modulating by a we call it spectral envelope. Okay, that envelope is a little bit more slowly varying in the spectrum domain, highly varying again in the spectrum domain. Taking the log, the whole values sort of shrinks a little bit. Okay, once it shrinks a little bit, now the original multiplication now becomes a summation. Okay? So multiplication becomes a summation. So it just shrinks a little, and becomes a summation. Okay. Now you take another inverse transform, then of course this sort of highly varying thing will somehow become here, and the slowly varying thing will be here. And then you can properly get the parts where you want. Okay. Let's look at an actual real case here. This is the waveform of vowel E. Okay, this is the capstone of the Q for C. Okay, this particular signal. Okay, so again you see the peaks approximately at the same places. Okay, the same periodicity as your signal. You can design a page extraction system on capstone as well, right? Because you see the clear peak here. You can do peak picking and try to find the differences. Or what you can do, like we did with the LPC, you can say, okay, let's take this signal, do another autocorrelation. Okay, then you can enlarge this kind of differences. Then you can do peak picking as well. Okay, so it depends on what you want to do, but we just know that this signal will have the same periodicity as this thing. The form coefficient here will correspond to largely the focal track or filter part of the coefficients. Okay. So some application we can design when we're in the domains of capture analysis. Okay, pigs in the caption, usually they operate at the fundamental period of the input voice speech. Okay, so what you can do is trying to do some picking in the velocity of the expected pitch period, okay, every 10 to 20 milliseconds. Of course, there are large issues that people try to design everything. Lego pigs doesn't mean there's always some voice. Okay, everything always influenced by your window type and length. Okay, and the longer it is, the shorter it is, the type of window you use. Okay, the silo, method, all those things will creep back in. Okay, because those changes your frequency component. What you're doing essentially, capture analysis is only taking the log, then do another transform. Right, taking the log and do another transform. Okay, so everything you know upfront, the operation you do with your Fourier analysis of the speech signal will have the same effect if you want to do it in the capture domain, because capture is the last layer transformation by inserting a log. Okay, that's it. So everything you learned in the past few chapters will hold here. Okay, typically a relatively small threshold are used for picking. Okay, pick occurs after other components dies out, and then there are tons of smart heuristics trying to set rules to say, okay, which pick is the right pick. Making sure you pick the right pick to be able to do pitch extraction. So many works out there. We're going to do format tracking. Okay, low time portion, right? Low time or low Q frequency or low time portion of the capture. They're ready to vocal track radiation while the post high time portion in the capture or high Q frequency portion in the capture. They're usually excitation. What you need to do is design some low time or low Q frequency lifter. Right? So you want to lift it out, then that becomes a smooth spectrum. Okay, so for example here. Okay, so these are the Q frequency. Okay, index, and if you just plot the 50, okay, not to the to 250, 400, 500, just a couple, 10, 20 is fine enough. Okay, and you replot this thing. Okay, so basically the difference between here, you just take the transform of this, right? How to get from spectrum to Q frequency? You take log and then do inverse transform. So what you can do is take the portion you want into a Fourier transform. Okay. Then, and if you want to do an original scale, then do exponential. And back to the, okay, if you take this part, low time part of the Q frequency, plot its frequency response, it will look something like this. Okay, very smooth spectral envelope. Okay, relate to formats. Okay, so those high oscillation points are gone. Okay, because those are the sourcing part are being thrown away. Because in the default, the small portions of the low time capture coefficient that relate to your filter. So again, capture analysis is a smart way of disentangling source and filter. Okay. The idea is a hypothesis on source exciting filter. Again, I want to point this out. Source and filter, this production, speech production is hypothesized. Okay, we don't really know if it's true. Okay. It's kind of how we understand our human physics, and then kind of, yeah, probably it's a source exciting a filter. Once that's set, all of these are designing based on that knowledge. Okay, so I want to repeat here is we don't really know. Okay, source exciting filter. That simple linear model is our speech production. Probably it's not. Okay, but because we engineer approximately like a source and filter model, hence you have all these tools. Signal processing tools that you design to say, okay, now I can tease apart this entangle source versus filter. Okay, I can look at the filter and I can design a way to track my formats. Okay, or I can look at the source. I can design ways to track my pitch and then all those sort of things. Okay, that all built upon a single one-point knowledge of we assume the speech that human produces follows a linear system assumptions of source exciting filter. Okay, so want to keep that in mind. So. If you ever have the opportunity to drill this down deeper, you'll see this approximation of linearity between our source and excitation. Source and filter excitation is actually not true in speech production. Our speech production is much more complex. But I think about how engineers are very clever. We approximate it linearly, then we do everything else. And then actually that approximation good enough for us to design so many technologies around speech. So let's keep that in mind. Okay, there's some useful diagrams. Okay, some computational complex capture. Now, the PDF IDFT to a complex log, and then IDFT you have a complex capture, or you have signal bouncing, or you have the SW, the Fourier transform version. The real part goes to log, imaginary part goes to argmax times the J, IDFT come back to the CN, and then you get back to the origin, the complex capture. Okay. All right, so we'll continue on. Okay, that's kind of a broad, quick dive into the capsular analysis. Okay, think about it's a new domain that can tease apart low frequency and high frequency convolution in the original time domain. Okay, make them linearly separable. Now knowing this capsular domain, we learned we call a parameterized model called LPC models. Okay, now we can start deriving we call the coefficient, or in machine learning terminology called features. Okay, called LPCC. Okay, linear prediction capsular coefficient. Okay, right. So we know capsular analysis gives us capsular coefficients. Fourier analysis gives us Fourier analysis. LPC model gives us LPC coefficient, those alpha filter coefficients. Okay. Now we can start combining LPC model to capsular analysis to give us LPCC coefficients. Okay, so that's now we start combining things that we know to start deriving the features. Okay, then the next step will take out LP, now becomes MF. Then those are the things that people know the best. Null frequency capsular coefficient. Okay, but now let's start here. LPCC, linear prediction capsular coefficient. Okay, let me first show a complete diagram of computing LPC, and we'll go into individual component and tell you the steps. Okay. Okay, so again, signal accounting, we'll go through we call a pre-emphasis block. We'll talk about this thing. Pre-emphasis block basically make sure our higher frequency information has a boost in the frequency representation. So otherwise, it goes down too small beyond your computer precision level, then you lost some track of your high frequency component. So some pre-emphasis, you think about this pre-emphasis. Okay, and then sorry, they do frame blocking. Okay, we have two parameters N and M, right? Frame blocking basically making our signal become short time. Okay, choose the segment, right? The length of the segment that you want to analyze. Choose M, how much you want to slide, how much overlap you want between the frames. Okay, so doing next, do a frame blocking. Now you have a blocked frame. Okay. A segment of the frame, as we call a short time signal. With a short time signal now, we apply a windowing function on this, right? So we can apply handing window, rectangular window, whatever we want. Okay. We have this windowing function. Okay. Right here, okay, we want to derive first the LPC coefficient. Now we know LPC coefficient can be computed multiple ways. Okay, one way to compute is, assuming you segment out a small segment of the signal, then by deduction, it becomes a normalized coefficient. That normalized equation can be computed recursively if you compute it like an autocorrelation function. Okay, so basically using the autocorrelation analysis, okay, depending on how much the pass order, right, linear prediction, how much pass sample you want to do, then you actually get the LPC coefficients. Okay, taking the LPC coefficient, right, you do this kind of LPC analysis here. Those LPC analysis we already know back in a few chapters back. We have LPC, those coefficients, those filter coefficients, those are poles, alphas, right? So if you remember it back here. Right, LPC model essentially is nothing here, just this part. Okay, it's an all pole model. Okay, so what those alpha you derive are all the CKs. So once you have that, then you can do a capsular analysis. Okay, capsular analysis takes them into a capsular domain. Okay, and then once you're in the capsular domains, then you can, the steps we'll talk about. We can do some temporal derivatives to make sure we capture the temporal differences between the coefficient across frames. Also, this is called parameter weighting. Essentially, apply a lifter. Okay, the lifter doesn't have to be rectangular. Again, imagine P. When you take a portion out of your caption, that means you apply a window function on your capsule. Okay, so when you apply rectangular, you just take it out. Okay. When you say I'm going to apply a window function, okay, so that it doesn't change too much of the frequency property of this capsule. Okay, that's a parameter weighting method of taking a segment out of their capsule. Okay, it's the same process as you are doing to your time domain signal. You take a segment of your time domain signal out. That's it, applying a rectangular function. Okay. That rectangular function we know has a high sort of a side lobe problem. Okay, same thing, right? As I told you, the capsule domain is just like time, but with a log in between. So if you want to take a segment out of your capsule coefficients, okay, when you take it, you're applying a rectangular function, okay, onto it. Okay, so if you want to make sure you don't want to have that many spurious frequencies and stuff like that, you might want to apply some weighted method of taking that segment out. We call designing the lifters. Okay, so you can, that's parameter weighting. Okay, parameter weighting. Okay, then once you have that, then you have the final LPCC coefficient. Okay, keep this loop in mind. Okay, we'll go through each block to compute LPCC. Okay. Then when we move on to the other coefficients, okay, the only thing that will change is here, right? Instead of looking at LPC model, okay, to derive my coefficients so that I can compute capstone coefficient, we can use other methods to describe the spectrum. Okay, if we describe the spectrum as the Mel scale, then that's the MFCC. Okay, if you describe the spectrum as LPC analysis output, then that's LPCC. Okay, if you don't do anything, just Fourier transform. Okay, that's just direct. That's a direct capstone analysis. Okay, so but the direct capstone analysis, you're not gonna. The reason why we do this because LPCC in this case, right? When we do LPC analysis, the alpha coefficient we already know an LPC coefficient that relates more to the filter, right? Okay, the spectral peaks of the thing. Okay, the error signal of the LPC analysis are the source. So if you do LPC analysis, what's left as the alpha coefficient, those related to the filter. And you take the filter to additional capsule analysis. Okay, it makes this filter become more filter-like. Okay, so basically make this capsule coefficient a little more clean. Okay, a cleaner version of it. Basically, you clean it once, right, and then clean it again. So it relates more to the filter part of the curve. If you don't do anything here, it'll have source involved. Okay, so that's the whole sort of speech analysis, speech coefficient computation. Effectively, always follow this same logic. Okay, and they just change different blocks. Okay, in terms of when you compute stuff. Okay, so again, repeat some of those things we already learned. Right? We'll talk about premises. We know short time. This is called short time. Okay. We know n and m, okay, especially the n. Okay, the length of the signal will give us the sense of we're doing a narrow band or wide band analysis. Okay, the windowing thing that we apply, okay, will change the side lobe leaks. Okay, and also the main lobe width. Okay, how precise you want to get the frequency. That choice you can make. Okay, this process is trying to do some frequency analysis, spectral analysis. The spectral analysis can be carried out just simply doing a spectral analysis, take FFT and then done. Or you say, I'll take a spectral analysis through the view of linear prediction model. Okay, the linear prediction model will give me a set of coefficients that tell me the spectral, the smooth up and downs, okay, not those oscillation points. Okay. So the LPC model helps me analyze the spectrum in a way that gives me that filter-like coefficients. Okay. Then you do another capsule analysis to make sure, okay, we're properly lifting out the low time portion of the frequency, okay, it makes it even more clean, okay, cleaner toward the actual filter coefficient. Okay. And why we need to do all these steps? Again, repeat, that's why I said the speech production concept of source exciting filter, okay, this linear combination is a hypothesized linear combination, okay, we don't really know. So as you combine more and more steps to clean up, okay, the filter, whatever remaining filter part is always, people will say, okay, that's more robust. Okay, now we'll go through each block and see. Okay, so first, let's recall this LPCC, okay, linear prediction capture. Recall the LPC model, right? L potential Z equals the signal divided by source, right? That's equals to G sum n, 1 minus sum k from 1 to P alpha k Z minus k. You just need to rewrite this polynomial form into a product rational form. Okay, that becomes the pole location. So LPC capstone is just the ZT inverse of the log of this thing. Right? So again, when you have all those methodology to compute, finally get this thing, you derive a filter looking like this. Okay, if you want to find the capstone of this thing, you just apply the capstone's formula to this thing. Okay, by inserting a log in here, then you get the we call it LPC capstone. And repeat, the better way to think about this, if you take my introduction to signal and system, they are all signal. Okay, we'll just talk about one of them as system because that gives us mindset better. Otherwise, signal and system, they are both signal. So this is a system. This is also a signal. So if you want to take a transform on this signal, we get a Z transform, we get a Z inverse, take a log. Okay, that's your capstone analysis. So the capstone of the LPC, okay, is basically ZT minus 1 log of H of Z. Okay. They are minimum phase. Okay. So this can be computed recursively. Okay, we already showed if you have the minimum phase signal, okay, all your poles and zeros are inside the unit circle, which LPC model is going to guarantee you to do that. Okay, then that particular capstone coefficient can be derived recursively using the formula we just derived earlier in the class. Okay, so your A hat of n LPC coefficient outputted from the LPC model equals A of n equals k from 1 to n minus 1 k divided by n A minus k A hat of k. And just grab yourself in your mind, okay? Linear prediction model, basically you're deriving this, okay? Rewrite this as a product form, okay? Now we want to find a capstone coefficient. Essentially, it's just a log of this version taking the Z inverse, okay? We know this particular form is a linear prediction model. It's an all-pole model. The poles and zero, there are no zero. The all-pole poles are all inside the unit circle, okay? So we know it's a minimum phase. Because it's a minimum phase, we can compute the capstone coefficient using a recursive formula. Now we already know the recursive formula, just plug it in and you're done. Okay, so we need to know the alpha n. How do we know the alpha n? You utilize the Lorentz-Durbin recursion formula to compute alpha n. Then use another recursion formula to compute A hat of n. So every signal that comes in through Lorentz-Durbin compute alpha sub n. Okay, the Lorentz-Durbin is basically building upon autocorrelation function, right? So what you need to do implement is just a set of autocorrelation function in the end. Some autocorrelation function, some version of that using the Lorentz-Durbin recursion give you alpha and plug into this recursion formula give you A hat of n, which is LPCC coefficient. Okay. So again, this is it's a one-liner. Okay, and hopefully it's not too difficult. Just make sure you string together the knowledge you already know. Okay. LPC is just a time series model, all-pole model, minimum phase. Okay. So capstone coefficient can be run recursively. Okay. The LPC computation itself. Okay. If you take the short time autocorrelation method, it is using the Lorentz-Durbin recursion. Okay. The Lorentz-Durbin recursion is a recursive formula. Every frame you want to find the LPC coefficient, you look at the past few frames, their autocorrelation function. Okay. By computing the autocorrelation function, you compute regressively. Okay, your alpha n. Okay. Once you compute every regressively alpha n, you can compute every regressively your A hat of it. Then you find the A hat of n, this LPC capstone coefficient. Okay. All right, so you want to make them into real capstone? Not too difficult. It's just A hat of n plus A hat minus n divided by 2. Okay. And then that's your final LPCC. Okay, usually it's a real capstone. Okay, so 0 and minus n less than 0 log of G equals 0, 2 C of n for n is greater than 0. Okay, so again, I want to stay on this page for a little bit, and then you try to go back home and then rethink everything you have learned. Okay, that's basically we start streaming everything. Okay, tie everything together into one particular methodology of computation, right? LPCC. Okay, it involves short time, it involves linear prediction, it involves autocorrelation function, it involves a recursion to compute the LPC. That coefficient. Then we know, because it's an all-pole model, that all-pole model has a minimum phase. Minimum phase can be computed complex capstone in a recursive formula. So there's basically 5, 6 different things put it together, you have eventually one single formula to compute LPCC. Okay, so this coefficient, we call it LPCC coefficient, and empirically people use them because when people start designing automatic speech recognition system, they first using Fourier transform, later they're using formant, they use various versions, use the LPC coefficient and so on. Eventually they found that this coefficient actually works quite well, okay, to do speech recognition system. And then we'll see an improved version of that is the MFCC we most know. But the LPCC really stay the first version of the actual working speech recognition system input is the LPCC. At this point, it's basically past couple weeks stuff. It now boils down to a single formula that you can compute the coefficients. Okay. All right, so let's go through each block quickly. Okay, pre-emphasis block. Okay, the speech spectrum has what we call a high frequency roll-off because of the Gaussian pole spectrum. Okay, if you do a pre-emphasis by making sure the higher frequency component are being boosted, okay, you can make the overall spectrum a little more flat. Otherwise, it has this kind of shape. Okay, less susceptible to finite precision effect. Okay, otherwise, when the value is very small, okay, it goes down to the precision that your computer can have, then that value practically becomes zero, which is not good because you do a series operation, like this plus that multiplied by that multiplied by this. Okay, all this multiplication you may make that value way too small. So you want to do a pre-emphasis. So pre-emphasis is very simple. It's just some a between 0.9 to 1. Okay, the filter is 1 plus AC minus 1. You plot this filter's response, it looks something like this. Okay, it gives about 20 to 30 dB improvement at omega equals pi, basically a high frequency component. Okay, so make this overall signal has a little bit boost in the high frequency component. Okay, the actual way of computing is just Sn minus A is hat n minus 1, right? So taking a signal minus a version of previous signal becomes the current signal. And by doing that, okay, you automatically boost a little bit of your high frequency component. So that's pre-emphasis filter. Now the next step is doing a short time LPC analysis of that pre-emphasized speech signal. Okay, so frame blocking. Frame length, you decide how many samples depending on sampling rate, how big, how wide of the window you're looking at, and decide whether there's a narrow band or a wide band kind of analysis. Okay, frame shift. Okay, that gives you the actual frame overlap n minus m samples. Okay. Usually you want to set m is less than or equal to n, so we call those things called sliding window. Okay, that makes the whole spectrum changes more smoothly. Okay, so we can write L frame of speech, right, equals to Sn times L plus n, right? So for n go from 0 to n minus 1, L goes from 0, 1, 2, 3, index which frame. Typical length people use usually about 20 to 40 milliseconds as your window length. Okay, n is about 10 to 20 milliseconds as your shift in the sequence. Okay. Again, we don't function once you frame block it. So you take think of implementation, right? The signal comes in, block it. Okay, so how many times I'm gonna take how many sample from my buffer. Okay, now send it to the next point where I have a window function I can apply onto it. Okay, so in this case we know you use our window function to smooth the signal at the beginning and end so that it doesn't drop to 0 too fast. So you can use Hamming or Hamming window. So that's Wn, which is window function. So you have x delta, which is xl of n multiplied by Wn. The most typical window function people use are the Hamming window. So again, your h of W of n equals 0.56 minus 0.46 cosine of this thing. Okay, so now you're going on to compute LPC. So you have autocorrelation method that you use on the window frame signal because all that process is doing a window frame signal. Try to get an LPC coefficient. Usually they're in the round 8 to 16. Okay, so what you need to do is find the sort of autocorrelation functions, like n from 0 to n minus 1 minus n. This filtered segment window multiplied by x l delta n minus n from 1 to p. So RL0 is a zero autocorrelation function, okay, and then so on and so forth. Then once you compute all this autocorrelation function, you can use Lewis interval recursion to get the actual alpha coefficient of your LPC models. Okay, Then once you have that LPC coefficient model, again, you plug it to get the LPC capture coefficient, depending on whether you're within the P or outside the P, you get coefficient like this. Okay. So again, this is an ZT inverse on the H of Z, okay, where H of Z is that all-pole model, the alpha coefficient coming out from the Lewis-Durbin recursion compared to an auto-pressure function on the segment of the window or of the window that you choose. Okay, so basically that entire steps gives you now the LPC coefficients. Okay. Typical numbers of capture coefficient you want to use usually is about 1.5 times the P order. Okay, if you have 8, then your Q should get you about 12 coefficient. These numbers are quite popular for your sampling frequency at 8 kilohertz. If you have more, then you might multiply that to the integer, right? So 16K, you might want to double that out. Okay, so that's the number of sample you look back at, the number of sample you actually get from your capture coefficient. Okay, so people do try to interpret what the capture coefficient really means. Okay, there's some study tries to do that, but it's still very difficult because there's so many operations having applied onto this thing. Okay, so at the first coefficient, people know that it's a zeroth coefficient probably is a measure of the average energy in the original signal. Like any transform, the first coefficient usually relates to some overall energy characteristics of the original properties. C1 seems to be some measure of spectral tilt. Okay, the C2 is some spectral energy concentration starting at various frequency component. Okay, so and so on and so forth. Again, but I feel like the capsule coefficient, the actual physical meaning start to become quite loose. Okay, it's very difficult to really know what each coefficient really means. Okay, you can imagine this basically it's a reparametrization. Okay, recharacterization of the original spectrum. Okay, but you don't really have an idea of what each really coefficient really means anymore. Okay, you kind of lose that physical interpretation, except for the first coefficient. Usually that means the overall energy of the signal. Okay, continue. Okay, aside from computing that particular frame, the capture coefficient, usually when we compute LPCC, you usually would also compute temporal capture derivative. So capture coefficient are good at representing what's happening at the, we imagine as the filter properties of the speech signal within that frame. Okay, but it doesn't have a property of capturing what has happened in the previous frame to this frame. Okay, so it's good at capturing local property. It's not quite good at capturing the temporal property. And we know in the speech sound, like you don't speak per frame in isolation. You speak sort of in a continuation. Okay, so there people do try to find first and second order derivative or deltas. Once you compute those coefficients, look at the past set of coefficients, find the acceleration and velocity, okay, and use those features as the representation of the temporal differences of that current frame. Okay, so we call that dynamic capture coefficient. Again, precise meaning is not become very elusive. Okay, so you're trying to compute how capture coefficient changes over time, right? How fast it's changing, okay, the acceleration of its changing, okay, and what that means in relation to the physical property of the speech production. That part is starting to become very, very loose because we have done too many mathematical operations on it. But it's started becoming the domains of math. We're just saying, okay, there's something in the past that I know the current capture is not capturing. Okay? So we want to find this capture coefficient and how it has progressed to this particular frame. Okay? Let's look at the first and the second order derivative and append features, okay, as a set of representation of the current frame. Okay. All right. So again, like I said, we pick a certain coefficient out in the capture domain. We call that process called lifting. In the diagram, we call it parameter weighting. Okay. Lower order capture coefficient are sensitive to the spectral slope because of the formula structure. Higher order capture coefficient sensitive to noise or the excitation source. Okay, so again, you want to make sure it's pick some art. It doesn't, it's minimizing some of the sensitivity of individual relationship. Okay, so some popular lifter that we use can be this. Depends on if you're lifting out total of Q capsular coefficient from the capstone. Okay, you can do think about this like window filter in the time domain. We call this parameter weighting lifter filter in the capstone domain. Okay, so it de-emphasizes the edge. Okay, repeat. When you pick a segment out, the real problem is not picking. The problem is the boundary. Okay, so if you want to make sure the boundary is as well taken care of, then the auxiliary frequency won't show up. Okay. So let's do a quick summary. So again, for every frame, right? Frame block it about 25 milliseconds, 30 milliseconds. Okay, you slide it 15 milliseconds. Okay, every frame, apply Hamming window, compute LPC coefficient, compute this capsular coefficient. Usually they become 8 to 16. Okay, then you find the first order delta and the second order delta. So usually, okay, if you have one, that's the C naught. Okay. You have 12 coefficient for your capsule. Okay, you find the first order delta adds another 12 coefficient. It adds another 12 of the second order coefficient, 66, 67, right? Or you can take 13 and then have 13, 13, 30, that'd be 639. Okay, so one thing you'll see quickly, if you run any speech recognition toolbox, if you compute LPC and this delta, and I always say I have about somewhere you'll see always the number between 30 to 40 features. Okay, it's because there's delta, 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 and the coefficient. Okay, people can extract between 10 to 13 capsular coefficient, then find their delta and delta, delta, put them all together, become a feature coefficient per frame. Okay, then that frame, you move on to the next frame, you recompute all that process to generate another 39 coefficient, generate another 39 coefficient, move another frame, generate another 39 coefficient. Okay, then slowly, once you start getting to this room, okay, we'll then take this as an input to a speech recognition system to say, okay, if I have this sequence of 39 coefficient coming in, how do I recognize this is R, E, U, L? Okay, then that's a machine learning, data-driven learning problem. Okay, we'll talk about that as we move into edge. But slowly, we're taking the speech analysis now to speech feature extraction. Okay, the feature extraction is not just feature extraction; it's basically built upon the knowledge that we know about speech, built upon the knowledge that we know about Fourier transform, Fourier analysis, Z transform, time series model, all these things. Okay, then become our tools to design methodology to eventually compute a set of coefficient to be used for a particular frame of speech signal. And then the reason I want to go through all this process is usually people find this part quite difficult. Okay, because there's so many background sort of undergrad courses you have to taken at some point. Okay, let's start to put it together. Okay, just for the purpose of you can fire out any toolbox, type LPCC net, LPCC, it gives you 39 coefficient immediately. You don't even have to know what's happening. Okay, inside that LPCC coefficient computation. Okay, but to be honest, if you want to understand how the speech signal actually will analyze it, find that feature, it builds upon this entire knowledge of signal and system. Okay, build upon the knowledge of linear algebra, build upon the knowledge of source and filter. Okay, build upon the knowledge of all of these things to eventually, and also the speech production knowledge. Eventually, people design a set of tools to say, okay, I can take any speech signal comes in, give me a set of features. In reality, if you open any toolbox, type one line tools, it gives you that coefficient immediately. Okay, without anything. Okay, so but just keep in mind this whole process of eventually deriving to this particular point of LPCC coefficient. Okay, so I'll stop here quickly today. So like Combi I would suggest, okay, again, go back and then try to understand speech analysis or a lot of this process, in a cohesive manner. So don't read them as segment to segment. Okay, so it's not one chapter. Usually, it builds upon what's known before. Okay, so it basically link back to we learn LPC, now we can do LPCC. Okay, if you just look at LPCC, you don't even know what LPC is. Okay, but if you don't know cash flow coefficient, you also don't know how to do that cash flow analysis. Okay, so all these things have to be combined. Okay, and also you need to kind of be aware. Okay, very fundamental things that people just do, right? Take a segment, right, when blocking the window and function. This thing don't just apply in time domain. Okay, that kind of same process apply in capstone domain. Okay, because this is the same thing. Okay, reading to the map. Okay, you'll find out. Okay, that in the capstone domain is actually a alternative time domain representation. Okay, so if you want to do any operation in that particular alternative time domain representation, you want to do it in a way that you already know what's best practice for the time domain operation to do the speech analysis. And all these things build upon speech production. Speech production are how we understand human produces speech, the source exciting filter, the linear assumptions of these two systems convolving with each other, and then try to tease them apart and try to find the representation for filter. Right. So that's why the capsule coefficient, the low time portion of the capsule coefficient, tells us the most about the filtering operation. Okay. So until the next time, we'll start talking about again move our viewpoint from speech production to speech perception. Okay, so we've talked quite a lot about how the human produces speech, the understanding of the speech, eventually using that knowledge to derive all these tools, okay, analysis to finally derive set of features. Now we'll talk about some basic understanding of how we human listens to other people's speech. Okay, how our ear functions. Okay, now by knowing the ear functions, then we can design other ways of computing the same set of coefficients. Then you have two different set of coefficients you can pick and choose to be the input of your speech recognition system. OK， 好，我们今天先讲到这边。